Welcome to the second video for Part 8 of our assessment series. In Part 8, we are looking at computerized adaptive testing, and in the second video for it, we are looking at the math behind implementation. So what we're asking is, which question gives the most information about a student's ability? And that information is going to be based on the parameterized fit. We talked about the RASH parameters before. I should have emphasized the difficulty, discrimination, the pseudo-chance level. These are not arbitrarily chosen by the teacher based on what they think are appropriate numbers for the question. We use norm referencing techniques, giving the questions to thousands of students ideally, possibly hundreds, but ideally thousands, and we use that information to figure out what the parameters are. We can then use those parameters to figure out which question in our database gives the most information about a student's ability. The information function itself is given here. Now, the p as a function of theta is the probability that a student with ability theta gets that question correct. So I as a function of theta is the information we have. And that dp over d theta in our numerator, that is the derivative from calculus. If we think about our information functions, and our probability functions in particular, these probability functions, they didn't give us much information. If you've got a grade 6 student, typical grade 6er, you give them a kindergarten question, it's almost insultingly easy. They're virtually guaranteed to get it. We don't learn anything we didn't already know. You give that same average grade 6er a calculus question, they can't do that either. Again, no surprises, we didn't learn anything we already knew, or we didn't already know. So we get the most information in the middle of that curve, when it's on that upswing. In other words, when the slope is steepest. And the derivative in calculus is the slope. We square it, so it doesn't matter if we're coming up or down at that point. We're just looking at the magnitude of the slope. And we're dividing it by the probability of getting it right and the probability of getting it incorrect at that point. So we can notice that this information function peaks at B. That's RASH's assessment for the difficulty level of that item. So when we're actually implementing the computerized adaptive test, the first step is to give the student a question that's appropriate to their grade level to start with. It's actually common to give them a question below grade level to help support nervous or weak students. So if you have a grade 6 student, you start them off with a grade 4 or 5 question so that they ease into it and have success right away, and then work from there. If that answer is correct, then you give them a harder question. If it's incorrect, you give them an easier question. And you continue this pattern until there's at least one correct and one incorrect response. Individual test creators can decide what algorithm they use to pick the next question, how far apart they are in difficulty. And that algorithm can get pretty sophisticated. Once you have both, then we can use other functions we're about to see. So you calculate the maximum value of the likelihood function, which we'll define on the next slide, and give an item at that level of ability. So the likelihood function predicts how likely is it that a student with this pattern of responses has a given ability. So we look at the pattern of responses and figure out which ability level is the most likely. That's the maximum value of the likelihood function. That's the ability level of the question we want to give them next. So we keep using that likelihood function to figure out the next item until the test is complete. Now, if you have a 3-parameter fit, you can actually get an ambiguous likelihood function. So we often limit to 1 or 2 parameters. This still works very well with high-quality test items. Even with just 1 parameter, you can still get a really good test. But if you have, as is very common, a student who gets an easier question wrong and a harder question right, then you can run into mathematical ambiguities. So the likelihood function itself, assume that the student has answered n questions. That's just the number of questions so far. you make a list of all the variables, u1 through un, where each variable is 1 if they answered that question correctly, and 0 if it was incorrect. So if they have answered 2 questions so far, they got the first right and the second wrong, u1 is 1, u2 is 0. With that definition, the likelihood function is going to be the product of the probabilities of getting it right times the probabilities of getting it wrong, where the exponents are either 1 or 0. Remember, an exponent of 0 gives a value of 1. So we're either taking the probability of getting it right when they got the right answer. Okay, so looking at this structure, for each value of j, so for each question, we will either have pj, if they got it right, or 1 minus pj, if the student got it wrong, as the probability. Now, since pj is the probability of getting it right and everything is either right or wrong, 1 minus pj is the probability of getting it wrong. And if the exponent will either be 0 or 1, depending on whether uj equals 1 or 0, so 1 minus uj, if the question is correct, would bring that exponent to 0, so the whole thing equals 1, and so forth. It's one or the other in our product. So finding the maximum does require calculus. It can be challenging to calculate it quickly, although practically speaking, if you take the log, well, then the product becomes a sum and the maximum will happen at the same place. So that does make it a little easier to calculate mathematically. So once you are moving, you can stop when you hit a certain minimum error value or a specified number of questions have been answered. If you're stopping after a specific number of questions, it's usually because that target was based on the standard error already. This is particularly true if your questions are set up with one parameter. Then you can sort of pre-compute how many questions it'll take to get to the standard error we're looking for. That standard error itself is seen here, so it's 1 over the square root of the sum of the information functions. So, all this said, we have one lesson left in our 9-part series. So part 9 will deal with non-parametric item response theory. Please join us for that.